Hello everyone, my name is Matthew Eliazar, and today I'll be presenting my final project on predicting heart disease using machine learning classification models. Over the next several minutes, I'll walk you through how I developed and compared four distinct predictive models to identify patients at risk for heart disease. Now let's get started. Let me begin by explaining why this problem matters and what I aimed to accomplish. The business problem that we're addressing is significant. Heart disease is the leading cause of death globally. It claims 17.9 million lives every single year. Early detection is absolutely critical, but it's often delayed, resulting in preventable deaths and escalating healthcare costs. Now, currently, traditional risk assessment relies heavily on physician judgment, which can vary in accuracy from doctor to doctor. Now, let's look at the background on the data. I used the Cleveland Heart Disease dataset, which contains clinical measurements from 297 patients. This includes demographics like age, sex, and vital signs like blood pressure and heart rate, and various other diagnostic test results. Now, this rich dataset provides an excellent opportunity to build predictive models that can assist healthcare providers in identifying at-risk patients much earlier in the disease process. Now, my project objectives were fourfold. First one is to develop an accurate classification model to predict whether or not heart disease is present. Second is to compare multiple machine learning models to identify which model performs best. Third is to provide actionable insights on the key risk factors that drive heart disease. And finally, fourth is to deliver a reliable clinical decision support tool that can improve patient outcomes and help hospitals optimize their resource allocation. Now, with these objectives in mind, let's look at the data. Now, let me describe the dataset that I worked with. The dataset includes 13 predictor variables that fall into several categories. We have demographic information like age and sex. We have clinical measurements including resting blood pressure, cholesterol levels, and maximum heart rate achieved during exercise. We also have results from diagnostic tests like chest pain type, fasting blood sugar, resting ECG results, and whether the patient experiences exercise-induced angina. Finally, we also have some advanced cardiac metrics like ST depression, which is measured by the old peak value, the slope of the ST segment, and the number of major vessels colored by fluoroscopy, which is the CA variable, and the thalassemia type. Now, all we care about is that these 13 features give us a comprehensive clinical profile for each of our patients in our dataset. Now let's see what patterns emerge when I explore the data. Before building any model, I conducted a thorough exploratory data analysis and pre-processing. Now let's start with the data quality. The good news is that it was a complete dataset with no missing values across 297 patient records. All 13 clinical features were retained for modeling after I validated their clinical relevance. I did apply a standard scalar normalization to the continuous variables for things like age, blood pressure, cholesterol, heart rate, and ST depression, mainly because these features operate on very different scales, and normalization is especially important for distance-based algorithms like what we'll see later, like k-nearest neighbors. Now, looking at the target variable distribution, class 0, which represents no disease, had 160 patients, or 54% of the dataset. Class 1, which had the disease present, had 137 patients, or 46% of the dataset. This relatively well-balanced dataset minimizes any class imbalance issues that could bias model predictions towards the majority class. Now, my data pre-processing steps included a 70-30 train test split with a fixed random state for 42. For reproducibility, meaning that anyone can run my code and get the exact same results. Feature scaling was applied to ensure distance-based algorithms performed optimally. Now, as I mentioned earlier, all 13 features were retained on both their clinical relevance and the correlation analysis that I performed. I have detailed EDA analysis in the appendix, which included correlation heat maps and box plots comparing diseased versus healthy patients, which I highly encourage you to review. But the key takeaway from my EDA is that features like thalassemia type, the number of major vessels, the maximum heart rate, and chest pain type showed the strongest correlations with heart disease. Okay, now that we understand the data, let's talk about the modeling approaches that I used. I tested 4 different machine learning models to find the most accurate method for predicting heart disease, and let me walk you through each one of them. Our first model is logistic regression, and what it does fundamentally is calculate the probability that a patient has heart disease based on their clinical measurements. The key strength of logistic regression is that it's relatively easy to interpret. It shows you how much each factor, like age or cholesterol, increases or decreases disease risk. We can even calculate odds ratios, which I'll show you in the next few slides. The trade-off is that it works best when relationships between variables are relatively straightforward, and it may miss more complex or non-linear patterns in the data. Our next model is K nearest neighbors, or KNN. This algorithm classifies each patient by looking at the 13 most similar patients in the training data. Now, the key strength here is that it naturally captures complex patterns without making any assumptions about the underlying data distribution. The trade-off is that it requires careful tuning to find the right number of neighbors. Now, in my case, I tested values from 1 to 29, and I found that k equals 13 gave the best performance, which I'll show more later in the appendix. Our third model is one of two tree models, which is random forest. Now, this approach creates 200 decision trees that vote on whether a patient has a disease, and the majority wins. The key strength of random forest is that it's highly accurate and it handles complex, non-linear relationships very well. It is also resistant to overfitting because of its ensemble approach. The trade-off, though, is that it functions somewhat of a black box, and it's hard to explain to a doctor exactly why a specific prediction was made. Although we can still extract feature importance rankings, which is also shown in the appendix. Now, our last model, which is another one of our tree models, is XGBoost, which stands for Extreme Gradient Boosting. Now, this technique builds decision trees sequentially, with each new tree learning from the previous tree's mistakes. Now, the key strength is that it is a state-of-the-art algorithm that wins many machine learning competitions, and includes built-in safeguards against overfitting. It is an unsupervised model after all. However, the trade-off is that it requires more fine-tuning and can be sensitive to parameter choices. Now, all four of the models were trained on the 207 training patients and then tested on the 90 unseen patients. I compared them using multiple metrics such as accuracy, precision, recall, F1 score, and AUC, which measures the area under the ROC curve. This comprehensive evaluation allows us not just to see which model performs best overall, but also to see which one excels in specific areas that matter for clinical decision making. So let's look at how each model performed. The results are actually quite revealing. So looking at the performance table summary below, the K nearest neighbors achieved the highest accuracy at 84.4%, which classified 76 out of the 90 patients in the test set correctly. Random forest came in at a very close second, 83.3%, just 1.1 percentage points behind. XGBoost achieved 80% accuracy, and logistic regression came in at 78.9%. Now, accuracy alone doesn't tell the whole story, so let's look at the precision and recall for each class. Now, for class 0, which is patients that did not have the disease, KNN achieved 85% precision and 85% recall. This means that KNN predicts someone doesn't have the disease. Like when KNN predicts someone doesn't have the disease, it's correct 85% of the time, and it successfully identifies 85% of all patients in the data set. Now for class 1, or for patients with the disease present, KNN achieved 83% precision and 83% recall. When it predicts that someone has the disease, it is correct 83% of the time, and it successfully identifies 83% of all disease patients. Now, I believe this relatively balanced performance across both classes is exactly what we want. The model isn't biased towards one class or the other. Now, looking at the F1 score, which is the harmonic mean of precision and recall, which is like a balanced mean between both, KNN scored 0.84, which is excellent because Even though all models showed consistent performance across both classes, with no major imbalances that should concern us. The key observation here is that all models performed well above random guessing, which would be about 50% in a balanced dataset like this. This demonstrates that the clinical features that we're using, things like chest pain type, number of vessels, and maximum heart rate, those features have real predictive power. From a clinical perspective, KNN's 84.4% accuracy means that it correctly identifies approximately 4 out of 5 patients, which provides substantial decision support for clinicians making risk assessments. But let's look at another important metric that tells us more about discriminatory power. Now, I want to show you the AUC scores, or the area under the curve scores of the RUC curve. This measures the model's ability to discriminate between patients with or without heart disease. Now, like I mentioned earlier, AUC stands for area under the RUC curve, and it's an extremely important metric in medical prediction because it classifies model performance across all possible classification thresholds. Excuse me, and not just one cutoff point. Now let's look at the rankings. KNN again takes first place with an AUC of 0.84%, which indicates an excellent discrimination power. Random forest, which is second, is at 82.2, which is also excellent. Logistic regression comes in at 0.79, which is an acceptable level of discrimination, and XGBoost is also at 7.799, which is also acceptable. Now, okay, let's ask ourselves, what does an AUC of 0.844 actually mean? It means that there's an 84.4% probability that if we randomly select one patient with heart disease and one patient without heart disease, our KNN model will assign a higher disease probability to the patient who actually does have the disease. Now, that's very strong discriminatory capability. Now, to put this in perspective, an AUC of 0.5 would be no better than just random guessing. It's like flipping a coin. An AUC of 1 would be perfect discrimination. Our best model at 0.844 is much closer to perfect than to random, which is ideal for our real-world data set. Now, we can see that all of our models exceed 0.79, which indicates that the features that we're using, the clinical measurements, the diagnostic tests, and the patient characteristics are genuinely informative for predicting heart disease, and this gives us the confidence that these models could provide real clinical value. The RC curves themselves, which I included in Appendix C, plot the true positive rate versus false positive rate across different threshold settings. The KNN's curve stays closest to the top left. Actually, I'm going to go over that later. Now, while KNN gives us the best predictions, there's tremendous value in understanding why predictions are made. Now, that's where logistic regression provides unique insights. We're going to go into the odds ratio of our logistic regression model that we used earlier. Now, even though KNN achieved the highest accuracy, logistic regression offers something incredibly valuable: interpretability. Now, this slide contains shows all the odds ratios for the features that we care about, which tells us exactly how much each clinical factor increases or decreases the risk of heart disease. Now, let me walk you through the most important findings. Our strongest predictor by far is CA, or the number of blood vessels colored by fluoroscopy, with an odds ratio of 4.05. What this means is that each additional vessel that's colored, which fundamentally indicates a blockage of the vessel, it increases a patient's odds of having heart disease by 305%. This is a massive effect and confirms what cardiologists already know. The more black vessels you have, the more serious your condition is. Second is sex, with an odds ratio of 2.62. This tells us that males have a 162% higher odds of heart disease compared to females, holding all other factors constant. This aligns with extensive medical research showing that men are at higher risk for cardiovascular disease, especially at younger ages. Third is thal, or thalassemia type, with an odds ratio of 2.26, meaning that a thalassemia abnormality increases odds by 126%. Now, I did some online research on this, and thalassemia is a blood disorder that can affect oxygen delivery. And this result shows that it is a significant risk factor for heart disease. Resting blood pressure, or TRS BPS, has an odds ratio of 1.86, meaning that higher blood pressure increases disease odds by 86%. Now, this is a well-established risk factor that doctors routinely monitor. Old Peak, which measures ST depression on an ECG, has an odds ratio of 1.70, meaning that greater ST depression increases odds by 70%. I think this is a critical diagnostic indicator that shows that the heart muscle isn't getting enough oxygen during exercise. Now, there's another interesting protective factor, which is the FALC, or maximum heart rate achieved, and it has an odds ratio of 0.48%, meaning that a higher maximum heart rate actually reduces disease odds by 52%. In other words, patients who can achieve higher heart rates during exercise tend to be healthier. This makes physiological sense. If your heart can work harder, it's probably in better condition. Now, these odds ratios generated by our logistic regression model are extremely valuable for clinical decision making, because they don't just tell us who is at risk, they tell us why and by how much. A doctor can look at the patient's test results and understand that addressing high blood pressure or investigating those colored vessels should be top priorities. Now, let's dig into where our models make mistakes and what that means clinically. Understanding where models make errors is just as important as understanding where they succeed, especially in healthcare, where different types of errors have very different consequences. Now, this table below shows the confusion matrix in tabular form, resulting from all of our four models. Now, let me explain what these numbers mean using KNN as our example, which is our best performer. Now, KNN correctly identified 41 patients not having the disease. These are true negatives. It also correctly identified 35 patients as having the disease. These are true positives. So far, so good. But it made 7 false positive errors. That's 7 healthy patients it incorrectly flagged as having the disease. In clinical terms, these patients would undergo additional testing, maybe a stress test or an angiogram, only to find out they're actually fine. This creates anxiety and cost, but it's not catastrophic. However, the more concerning result that we had is the 7 false negatives. Now, these are patients who actually have heart disease, but the model predicted that they were healthy. Now, this represents 17.6% of the 42 disease patients in our test case. Now, these are patients who might not receive the treatment that they need because we missed them in the diagnosis. Now, in healthcare, false negatives are typically more costly than false positives, and meaning missing a disease can lead to disease progression, heart attacks, or even death. On the other hand, a false positive just means that we just need to do some more extra testing. So when evaluating these models, we need to pay special attention to minimizing false negatives. However, like comparing across models, KNN achieved the lowest number of false negatives at just 7, tied to Random Forest at 7 as well, though Random Forest had 8 false negatives actually. I'm sorry, let me correct that. Random Forest had 8 false negatives. Logistic Regression had 8 false negatives, and XGBoost had the most at 9 false negatives. So from this table, we can see that KNN strikes the best balance. It minimizes the dangerous false negatives while maintaining strong overall accuracy. This is exactly what we want in a clinical screening tool, catching as many disease patients as possible while maintaining good specificity for healthy patients. Now let me bring this all together for my final recommendations. So, based on this comprehensive analysis, I'm ready to make clear recommendations for implementing these models in a clinical setting, wherever that's relevant and possible. The winner here, quite obviously, is k nearest neighbors with k equals 13 neighbors. Based on evaluation across multiple metrics like accuracy, AUC, precision recall, and our confusion matrix analysis, KNN emerges as the superior model for heart disease prediction. Now, let me summarize why. It achieved the highest accuracy at 84.4%. It achieved the best AUC score at 0.844%, indicating excellent discriminatory power. It showed balanced precision and recall with an 84% macro average across both classes, and critically, it had the fewest false negatives at just 7 missed diagnoses, which is important from a clinical safety perspective. Now, why do we think KNN outperformed the others? First, I think it successfully captured complex nonlinear relationships in the clinical data that simpler models like logistic regression couldn't detect. Second, the optimal K of 13 neighbors was identified through a hyperparameter tuning, which I demonstrated in the appendix. Third, the feature scaling that we applied enabled effective distance-based classification. And fourth, KNN's local pattern recognition is well suited to heterogeneous patient populations, where different combinations of risk factors might indicate the disease. So my recommendations are as follows: to deploy KNN as the primary screening tool in clinical decision support systems in a theoretical world where that's appropriate. This model should be integrated into electronic health records so that when a patient's results are entered, the system can flag high-risk individuals for closer follow-up. We can also, secondly, deploy a random forest model as a backup because of its 83.3% accuracy for validation and ensemble approaches. We can continue using logistic regression for interpretation despite its lower accuracy, but its main value proposition is the odds ratio that it provides, which is invaluable for understanding why patients are at risk. Fourth, we should focus on clinical interventions on high-risk indicators that we've identified, like the number of vessels colored by fluoroscopy, patient sex, especially male patients, and the thalassemia type. These are the factors with the highest impact on disease risk. The expected impact of deploying this model is significant. With 84% accuracy, we can enable early identification of approximately 84% of at-risk patients. This could significantly help hospitals by lowering mortality rates and lowering healthcare costs. Now, some important next steps for full deployment is that the model should be validated on other external data sets from different hospitals and different populations to ensure that it generalizes well. We should implement real-time prediction interface that integrates seamlessly into clinical workflows. I think a more formal cost-benefit analysis should be conducted to quantify the financial impact, and we might explore different ensemble methods that combine KNN with random forest to see if we can push accuracy even higher. Well, in conclusion, this project demonstrates that machine learning can provide powerful decision support tools for healthcare providers, potentially saving lives through earlier detection and intervention. The models that I've deployed thus far, I believe, are ready for pilot testing in a clinical environment, with KNN as the recommended primary algorithm based on our analysis today. Now, before I close, I want to point out that I've included comprehensive appendices with additional analyses. Like I mentioned earlier, detailed EDA results with correlation heat maps and feature distributions, all our ROC curves compared side by side, and the systematic case selection process that led me to choose K equals 13, random forest, feature importance rankings, and raw data samples. These provide complete transparency in my methodology, and I encourage you to view them for full analytical depth. Thank you so much for your attention. I'll go over the appendix real quick. Here's an example of our data set. Here is the correlation heat map of the different features and our target variable for heart disease. Here's the EDA results of age distribution of people who do have and who don't have the disease. Here's the box plot of maximum heart rate of those who do and those who do not have the heart disease. EDA results for ethnic depression and old peak with those who do and who don't have the disease. Really interesting graph. Our ROC curves for all the models that we've used and their area under the curve in the legend as shown below. My K selection process and how I fine-tuned K to yield k equals 13, and the future importance for our random forest.